Okay. Hi, everyone. Thanks for coming. My name's Jennifer Schrack. I'm a professor at Hopkins, and I'm going to be talking about wearables and research today, specifically about aging research. I'm going to turn my camera off just to make sure the video or the presentation is the best it can be, but I'll come back on when I'm done. And I will say that you don't have access to the chat, but you can post questions in the Q&A. And I'll try to keep track of them as we go and answer as many as I can. Okay, so a little bit about me to start. So, how I got into this area. I am an exercise physiologist by training. I did my master's in kinesiology at University of Michigan. And that actually is what got me interested in aging and movement and health. And so after I did my master's, I worked at the National Institute on Aging, working specifically on the Baltimore longitudinal study of aging for a little bit. And that was my introduction to epidemiology. And so then I did my PhD in epidemiology at the School of Public Health. I finished there in 2011 and returned as faculty the following year in 2012. So I've been faculty for going on 15, or I'm sorry, 13 years. And I'm a professor in the Department of Epi. I'm also the director of the Center on Aging and Health. And I'm the MPI of the National Health and Aging Trends Study, also known as NHATS. And we also run a research group called Engage, out of the Center on Aging and Health, and that stands for Energy, Activity, and Aging. So that's a little about me. And so today I want to talk about wearables, but I want to take a step back and think about why they're important in aging research. There's a lot of reasons, but my personal interests are really centered around movement. So this stems from my background in kinesiology and just how my fascination with movement and how it is protective for health. So we know physical activity is good for us, but it's also a sign of how people are faring as they get older. And this crosses species. So from worms to fish to mice, anyone who has a dog and as the dog gets older, it walks so slowly. You know that these things change across species. And of course, with humans, we know that as people age, they move differently. And the most consistent change in age-related movement is this decline in usual gait speed. So throughout life and up until about age 60, most people walk at a speed of 1.1 to 1.3 meters per second. But by age 80, that's slowed to be an average of 0.85 meters per second. So that's quite a bit slower. And this decline is predictive of negative health outcome. There's a ton of literature in this area on gait speed or walking speed and health. And it's been linked to when people get below 1 meter per second, it's been linked to disability and mortality. Less than zero point 0.8 meters per second has been associated with frailty and disability, and less than zero point 0.6 meters per second has been coined as dysmobility. So kind of disability specific to mobility. And so what you see on the right side of the screen is usual gait speed over a 7 meters. You see gait speed on the y-axis and age on the x-axis. And you can see what I was just saying. Throughout life, it's pretty level until around the age of 60, and then it starts to decline and really trail off after people are in their 80s. And this is men and women. Men are the black line and women are the gray line. Men tend to walk a little faster just because they're taller and have longer legs. And then women tend to be a little slower. So we see it's in both sexes. This is data from the Inchianti study. And we measure this slowdown in many, many ways, and most of them are in the clinical and laboratory environments. So things like treadmill speed, people get on it and we say, okay, push the up button until you're at a comfortable speed. Usual gait speed over 3 to 6 meters, which is data like I just showed you from Inchianti. There's things like the 2 minute walk, the 400-meter walk, the 6 minute walk. Those are all kind of walking endurance tests. They can be fast or slow, usual paced. There's timed up and go, which is used clinically. There's a narrow walk, which assesses balance as well as gait speed. Then there's a fast-paced walk. And then there are things like gait labs, which is this picture in the lower right-hand corners. And I know a lot of people associated with AITC have a lot of interest in gait. And these labs are very sophisticated and can test things like speed, variability and stability. So the picture here, this is actually from the BLSA Gait Lab, and this is Dr. Metter, who used to be the chief medical officer there, and he's got the balls all over him to really detect how fast he's moving and also different aspects of his gait mechanics. So let's see, there is a question in the Q&A from Jose. It says, besides wearables for biometrics, is there a wearable that allows an elder to chat, specifically to receive voice messages and respond accordingly? Jose, I'm sure there is, but that's really kind of outside my realm of expertise. Um, I know there are a lot of people working with voice and what voice can tell us in terms of cognitive domains, but I don't really know specifically about wearables to collect voice. So all of these measures work really well. They've been used, like I said, extensively in research, but also they're all stable and done in the lab, in the clinic, and they're all done in what we would think of as optimal conditions, right? So there's no cell phones, there's no kids, there's no pets, there's nothing to trip over. These are all like optimal conditions. So when we test people's performance in the lab, we're getting what we hope or think is their optimal performance. This is the best they can do. But it's not really representative of what they actually do in the real world. And so this has been a problem for a while because we really want to understand gait speed better. So this is gait speed from the Baltimore Longitudinal Study of Aging. This is unpublished data, but this is just showing you the same thing that I showed you earlier from Inchiante. This is men and women, and we see usual gait speed and how it declines throughout life. But I want you to notice the scatter and notice that when we color code it by speed, it's not uniform. And by that I mean not everybody gets slow with age. Now, if you look out here around, 90, 100, certainly all those people are moving pretty slow. But after 60, up until about the age of 90, there are quite a few people that are moving in what we would consider normal range. So not everybody slows down as they get older. And I think it's really important for us to try to understand who walks faster and why, and what that means in terms of health as people get older. And so, like I said, we do a lot of functional ability in the lab. We look at ability and time to complete with usually with a stopwatch. And again, as I said, that's their optimal performance. We also get self-report measures, which are important because they give people's perception of how they're doing. We ask them about their ability to walk a certain distance and how difficult it is. And that is actually considered the gold standard for assessment because we're asking people about how they function in their own environment. So in their home, in their neighborhood, if they're walking down the street, and so on. But how can we do this more objectively? Because perceived performance is important, but often it can be incorrect because a lot of times people don't really know. If you ask them, can you walk a quarter of a mile? They may have no idea. So it's all, we really optimally like to be able to combine an objective measure with a real world measure. So how do we understand real world performance? So this is where sensors come in, and this is where a lot of my interests come in. Sensors, and what I mean by sensors specifically is these kinds of things, wearable devices, mainly accelerometers. Most people know them by the commercial ones, which I'm showing on the left side of the screen. So things like Apple and Garmin and Fitbit. I mean, there's been a lot of iterations of these things. They've kind of settled down a little bit. I don't know if anybody remembers the early Fitbits, the ones that you could clip onto your belt or your pants or your shoe or wherever you wanted to wear it. They're still, I think, out there, but they've really largely been replaced by wrist-worn devices, smartwatches, things that do more than just monitor steps. They also tell us who called us and who's texting us and things like that. In the middle of the screen, these are kind of not as common, but people will be more familiar with some of these. A pedometer, old school pedometer, they've been around a long time, and that really just has a mechanism that counts the up and down motion that's associated with a step. Even if you don't have any wearables, you probably have something in your phone that's tracking how much you move. And then there's also things like the Aura Ring, which I haven't personally worked with, but I know a lot of people in the sleep world are very interested in this device. So it's a ring that people wear that can give some similar data. On the right side of the screen, you'll see what we know as research grade devices. So this is a lot of what we use in research. So this is things like Actigraph, Gene Active. This blue one up here is a Activity that was used by the UK Biobank. There's ActiCal, which was a very popular hip-worn device. And then here at the bottom, we have ActiWatch, which is made by Philips Respironics. They actually just stopped making it and was very popular with sleep researchers. And then here on the right in the lower corner, we have the Actigraph Leap. That's their brand new one that measures how much people move, but also has photoplethysmography, which is the sensors in the back that can tell us things like heart rate, skin temperature, and oxygen saturation. So these things are getting fancier. They've been around. And we as researchers really need to understand how to capitalize on these and understand health better. So, like I said, they're here to stay, and it's a very profitable industry. So, this is the global wearable sensors market, kind of where we were in 2024 and where we're projected to be by 2032. And you can see it's just a huge market. And this is mostly consumer, but this is also true of healthcare, pharmaceutical companies, and other things that are interested in using wearables to understand health better. And you can see the accelerometer is the dark purple area. So, it's probably one of the larger parts of the wearables market. You can see optical is coming along, but there are other sensors as well, so probably voice and things like that. Where we are in terms of research, so this is actually becoming outdated at this point. I actually asked my research associate to help update this, but this is from a paper we published back in 2018, just looking at the frequency of PubMed manuscripts with the keywords accelerometer and older adults, and from 1987 to 2017 to just demonstrate how much these things have really exploded in terms of the research world. And so when they were around in the early, late 80s, early 90s into the 2000s, it was mainly these big devices. There was like the mini mitter and there was the logo mitter or something like that. And they were bigger. You wore them. I wore one when I was in grad school at Michigan. It was like a fanny pack that I ran around with. They were bulky. People didn't like wearing them. And the data was really complicated. But as they've gotten smaller and more easy to use, you can see they have really taken off in terms of research. So, what have we historically done with this data? So, when the first large scale study to really use accelerometers was NHANES, and they used a hip-worn actigraph similar to the one that you can see in the upper right corner of the screen. And this is a snapshot of NHANES data, which I'm providing just as an example for what we really did with this data when these things were first released. So a lot of exercise physiologists wanted to use this to understand compliance with public health recommendations for daily physical activity. So what you see here is activity on the y-axis, and on the x-axis we see time of day. So from about midnight till about 8 a.m. you don't see anything, and that's because they didn't wear it while they slept, because this was a hip-worn device and people would take it off at night. And so they were instructed to wear it during waking hours. So you can see around 8 a.m. this person got up, and you see a lot of spikes throughout the day. The higher the spike, the more intense the movement, the lower the spike, the less movement. And then researchers developed thresholds, what we call cut point thresholds, to define the intensity of the movement. So if it was up here between the blue and pink line, that was believed to be vigorous intensity. If it was between the red and blue lines, that was believed to be moderate intensity. And then if it was below the red line, that was believed to be light intensity. So they'd carve the data up to estimate compliance with recommendations to be physically active, which is about 150 minutes of moderate to vigorous physical activity per week. So that can be simplified to about 30 minutes most days of the week. And so people wanted to understand within NHANES, were people meeting these recommendations? And so this is probably one of the most famous papers. It's been cited many thousands of times that came out of that original data. And this was led by Rick Troiano, who was at NCI at the time. He's since retired. He really pioneered a lot of the work that was done in physical activity measurement with accelerometers. But the main conclusion from this paper was that among adults, adherence to the recommendation to attain 30 minutes a day of physical activity is less than 5%. So it's like, wow, we're really not doing what we're supposed to do in terms of physical activity as a nation, right? So NHANES is supposed to be representative, and it's got children, adolescents, and adults. And I want you to note here, if you can see right above the text, it says adults are 20, everybody over the age of 20. 20 and older is considered an adult. So there was no consideration given to speed of movement and aging and capacity or anything like that. And in fact, if you dig a little deeper into this paper, it noted that older adults, those age 60 and over, only about 2.4% of people in that age range are meeting the recommendations. So the prevalence was about 2.4%. So I read this paper with interest, and I thought it was a feat that was very well done. Like I said, it was the large first paper to really take this on such a large scale. But I'm looking at that and I'm thinking, gosh, if we aren't meeting the recommendations. What does that say about us as a nation and our health? And then thinking specifically about the people over the age of 60, I mean, they're not meeting the recommendations, but that doesn't mean they don't move. And I really wanted to try to understand movement from these sensors a little bit better, especially with regards to aging. So I went back to thinking about this data and thinking, well, what about all this data we ignore, right? So we drew lines through the data to define cut point thresholds, which makes it easy, right? It makes it clinically interpretable. It makes it more understandable. But what are we throwing away here? Look at all these spikes. Look at the lack of spikes or the spaces where there's very little activity. What can we learn about that? How do we dig deeper? How do we make more sense out of this data? And what can it really tell us? So that led to the beginning of my interest in this data. And we started looking at simple accumulation metrics, so some things that are very easy, and then what we call diurnal patterns. If you're a sleep researcher, you might call it a rest activity rhythm. And I'm going to show you some of what we did in the early days with some of this data. So this was one of the first papers that we published as a group. And when I say we, at the time I started doing this, I was working at the BLSA as a postdoc at the NIH. And I was collaborating with a group here at Hopkins, Ciprian Kurnichanu, who's a professor in biostats, Vadim Zapunikov, who's a professor or associate professor now. At that time, he was also a postdoc, and then this group at the NIA. And so we had data from this device. It was called the Acti Heart. And it was a device that was chest worn with two electrodes to give heart rate and physical activity at the same time. And so we started with just looking at the physical activity data, and the best we could get was minute level data. And so we started just by plotting it as an accumulation of activity throughout the day. So what you see here is a lot of shading because there's a line for each person. And then this is cross-sectional data, but we divided it into groups of the green line is those who are under the age of 60. And the median age in that would be about 50. And then the red are 60 to 67, the blue is 68 to 74. And then this gold line is about 75 and older. And so what we saw here was four data-driven age groups, a line for each person. So first thing we see is there's a tremendous amount of heterogeneity in what people do. And then we see, not surprisingly, that as people get older, they're less active. And so again, it's cross-sectional data, but if you average it about out, from mid to late life, there's about, on average, a 1.3% loss of activity per year from mid to late life. So that's a lot. I mean, that really means from age, 50 to 100, you're going to lose more than half of your daily activity. You're going to move about half as much as you did in midlife. And so that's a big statement, and that's a lot of lost movement. We also took the data, same paper, same study, and instead of looking at it as total activity per day, we did an accumulation pattern. And so what you see here, because this was a chest-worn device, people wore it 24 hours a day. From midnight till about 6 or 7 a.m., we don't see much, and that's because they were asleep, we hope. And then throughout the day, they get up, they go about their day, they come home, and then they go to bed. So this is roughly a 24-hour average activity pattern in the same four age groups. And this we thought was really interesting because, as you can see, the two younger age groups and the two older age groups have drastically different patterns of movement. And it also is very interesting that the older two age groups, they seem to peak by noon and then really trail off. And so we started trying to pick this apart to understand what is this? Why is this happening? What does it mean? And again, as cross-sectional data, we did notice that those who were employed tended to be more active, but they also tended to be younger. So some of this could be retirement, people just not moving as much because they're not actively getting out of the house at the same time every day to go to work and do whatever their jobs were. But what about health conditions? We were also very interested in that. And so we started trying to pick this apart. This was a paper who was led by Amal Wanigattunga, who's an assistant professor in epidemiology, works really closely with me on a lot of things. So you're going to see his picture a lot. But at the time he did this, I believe he was a postdoc, so he was brand new to this area as well. And so we just started looking at it with fatigue and fatigability. So, do people move less, and do they peak earlier in the day if they have higher fatigability? And we did see that fatigability was really strongly associated with it. So, this is just their rating of fatigability or how hard something was after a 5-minute treadmill walk. And so, those who had higher fatigability definitely had less activity. They tended to peak about the same time at noon, but they never got as high and they tended to trail off earlier in the day. And so that was interesting because fatigue is a big problem for older adults and for people with chronic conditions, but it's really non-specific. Fatigue can tell us, it just tells us something's not right. It doesn't tell us exactly what. So we started to dig a little bit deeper and look at it with different conditions. So one that we've been interested in is cancer status. So people who've ever had a history of cancer versus people who haven't. So this was looking in the Baltimore Longitudinal Study of Aging. And so about 30% of the people there had a history of cancer. Most of these people were healthy survivors, nobody actively battling malignant cancer. And this is interesting because there's more and more people surviving longer, surviving cancer, which is great. But we also have to think about what the long-term effects of the treatment and things like that are. So they take these toxic treatments that they have to save their lives. But what is that going to do long term? We don't really know that yet. And so this was one of the first papers to look at that in terms of physical activity and their daily movement. So again, we see between midnight and about 6 a.m., not a lot going on because they're asleep. And then throughout the day, those without a history of cancer are the black line, those with a history of cancer are the red line. And we see that those with a cancer history tend to move less, and they don't get as high, and they tend to be, in terms of trailing off, it tends to happen a little bit earlier in the day. And when we averaged that out in terms of our regression modeling, we saw that the difference was equivalent to about 5 years of age. So that means that somebody with a history of cancer looks about 5 years older than someone without a history of cancer. So somebody who's 60 with a history of cancer looks more like a 65-year-old with no cancer history. Let's see, there's another question in the Q&A from Alexandra. Is this a specific age group or the whole population? So I don't know if this was in pertains to this slide or the previous one, but it's everybody in the BLSA that had these testings. I will say that the BLSA has people of all ages. We concentrate mainly on people over the age of 40 or over the age of 50. There are some young people in here, but it's mainly 50 and older across most of these slides. So that's a good question. Okay, another thing we looked at was physical activity and vision loss. So this was led by Yuan Kai, who's now assistant professor at Pitt. She was a postdoc who worked with me at that time. And this was interesting because we looked at both visual acuity and visual fields. And again, this is in the BLSA. And not surprisingly, those with vision impairment, so that's shown in the red, the dashed line, had lower physical activity. So on the left, you see visual acuity, and on the right, you see visual fields. And I don't think it's surprising that people who have impaired vision or tend to move less. They tend to be less comfortable with their surroundings. They're more cautious. They're more afraid of falling. So it's natural probably that they move a little slower and move a little bit less. But the interesting thing here, as you can see by the arrows I've inserted, is that the difference that was detected was much larger when we looked at the visual field test. And this is interesting because visual acuity is the test that is much more commonly done clinically. So that's the eye chart. So for those of you going to the eye doctor, you have the eye chart, you're having a visual acuity test. You can see that you can detect a difference, but the visual field appears to be much more sensitive in terms of understanding some of this difference. Adam's writing, in regard to the question earlier about language, there is the AGIR framework that combines 3D gait with large language models. Okay, thank you, Adam. It's good to know. Okay, next. And so then we've really gotten into cognitive diagnosis. So this is really interesting because cognition has really taken up a lot of steam in the last decade in terms of both attention and funding. With aging and disease, we've gotten really good at treating a lot of diseases, and we have surgeries and transplants and things like that. But we haven't figured out how to save the brain. And so one of the things we need to try to understand, and we've made a lot of strides, is how do we assure people age better in terms of their cognitive health? And so we looked at this physical activity diurnal pattern by cognitive diagnosis. So what you see here is the red line is people with MCI, mild cognitive impairment, or AD, Alzheimer's disease, versus those with normal cognition. So it's a pretty small sample who were cognitively impaired, only about 36 versus 549 with normal cognition. But there was a striking difference in terms of their daily activity pattern. And this was really interesting because when we just looked at one number, how active they were. So if you were looking at like total steps per day or total active minutes per day, and you just summed it up across the day, you're not going to see a difference after you adjust for age and sex and those kinds of things. But if you look at it across the course of the day, you get a lot more information. Because what happens is older people with MCI or AD tend to be a little more active later in the day and especially into the evening. And you can't see it very well here, but overnight they tend to be a little bit more active because they're not sleeping as well. So when you average the activity out across the day, it doesn't look like there's this dramatic difference. Whereas if you look at it in detail across the day, you can detect more important differences that could be clinically meaningful. We repeated this in the National Health and Aging Trend Study in NHATS simply because it's a more representative sample than the BLSA. And we also have some more information. This was led by Anise Davouti when she was a postdoc. It was actually just published recently online in Med Science and Sports and Exercise. And she's now transitioned to a faculty member. She's an assistant scientist in epidemiology department at Hopkins. And here in NHATS, we have some different classifications. We have those without dementia, and then we have possible or probable dementia. And so this is done with an algorithm. We don't have a clinical diagnosis. But we saw a very similar pattern where those without dementia tended to get up earlier, be more active throughout the day. And those with possible or probable dementia tended to get up a little bit later, and their activities seemed to extend more into later in the day in the overnight hours. And interestingly, this was with a wrist-worn device in NHATS, whereas this previous slide with BLSA, I believe that this was with the ActiHeart. So this was a chest-worn device. So it's interesting across placements and devices, we see a very similar pattern. Um, what is really interesting here is that possible or probable dementia looked the same. So possible dementia is something they scored like one standard deviation below the mean on one of the tests, whereas probable dementia was two standard deviation or a standard deviation on two or more of the tests. And so this is interesting because it shows that even in the earlier stages of dementia, the differences are there. And that made us wonder, may these differences in activity patterns and movement emerge in the prodromal stage of Alzheimer's disease when the pathology tends to show up? And we don't know yet. This is cross-sectional data at that time point, but we're hoping to dig deeper into that as we go. There's two more comments. Since there are more patients with long COVID than cancer and fatigue is leading symptom, particularly post-exertion malaise, or do you have pre and post-COVID data? We don't have a lot of pre and post-COVID data, Cheryl, and that's a great question. And that has come up recently in some other work we've been doing. And there's not a lot out there yet. I think we'll be able to understand that a little bit better more. It takes a while to get the longitudinal data in, but we should have some of that before too long in some of these cohort studies. And what is the algorithm for dementia? So you can find that on the NHATS website, Emily. So if you go on to, well, you could pull this paper by Anise, or you could also go in and pull it on the NHATS website. It's posted there. Okay, so next, so that's a lot of the work we've done with diurnal patterns. But the other thing that you'll see from this is the lines tend to be a little shakier for those with possible or probable dementia. And some of that is sample size, but some of it made us wonder, well, what can that tell us about transitioning in and out of active and sedentary states, as well as stability patterns? So, are people's activity patterns the same throughout the course of the day? And do they vary day by day and that kind of thing? So we went back to thinking about the NHANES data. So this again is our example data of one participant. And again, we see there's no activity overnight, but we see different spikes during the day. And this dotted line here is what is generally considered sedentary behavior. So these devices are really sensitive to movement. And even if you're sitting and watching TV, if you're moving around a little bit, it's going to pick up on some of that. So most of these devices have a threshold below which they, or a threshold at which they recommend classifying the data as sedentary versus active. And so we started thinking about each movement bout in terms of is it active or is it non-active? And so we kind of created this binary index thinking about how fragmented or broken up people's activity is throughout the day. And this is done in the sleep literature with sleep fragmentation. So anybody who's familiar with that metric, this is very similar. Looking at are they moving, yes or no? And then how long are they moving? So if they're moving, how many minutes are they moving for? And so what we saw when we started looking at this was that these transitions happen a lot, and they seem to happen more as people get older. So this is a picture just to kind of illustrate this in terms of to make it easier to wrap your head around. So a younger person could easily walk for 10 minutes without stopping, right? And so their fragmentation index would be really low. They're not breaking up their walking, they're just walking continuously. Whereas somebody who's a little bit older may walk for 8 minutes and then stop and rest and then walk the other 2 minutes. And somebody who's very old might walk for 5 minutes, stop and rest, 3 minutes, stop and rest, and then 2 minutes. So these people, importantly, are all accumulating 10 minutes of activity, but it's being accumulated in very different ways, right? And so does that matter? Do we care? And again, if you're just looking at total activity per day, like steps, or you're looking at active minutes per day, you're going to miss this, right? You're not going to understand how it's accumulated throughout the day. So we wanted to create this index. This is a 10-minute window example, but we want to do it across all days that people wear their device to get an average fragmentation index for each person. And so we did that, and this again is in BLSA, and you can see the age range here is about 30 up to close to 100, somewhere in the 90s. And we see that it really goes up with age, especially after the age of 60. So similar to what we saw with gait speed, it starts to really shift after the age of 60. And then we said, well, how does it associate with function? And so we saw that activity fragmentation, so how broken up their activity was throughout the day, was strongly associated with laboratory measures of function. So this first graph on the left, we see it's associated with gait speed. So 1 unit increase in fragmentation was associated with a 0.1 meter per second slower gait speed, and that is clinically meaningful. Similarly with fatigability, we saw that higher fatigability was, or I'm sorry, more fragmentation was associated with higher fatigability. So people who have higher fatigue have to stop and rest more. It was very strongly associated with time to walk 400 meters. So we would think about endurance capacity. On average, a 1 unit increase in fragmentation was associated with 31 seconds slower to walk 400 meters, which is a lot. And the expanded SPPB score, so short physical performance battery, we saw a quarter of a point decrease for a 10% increase in in fragmentation. We have another question here. Susan said, in experience with family MCI dementias, it seems vision impairments have impact on activity, not reassured with foot placements. Do you have data on this variable? So yeah, I did show vision earlier, Susan, and hopefully if you can get the slides afterwards, you can revisit that. But yes, vision and hearing and dementia all go hand in hand, as we know. And we've actually been looking at that, and not necessarily in terms of physical activity, but in terms of their mobility and how that's affected. Okay, so we see that fragmentation is associated with function, but we also said, okay, is it associated with mortality? So Amal went back and looked at this data and looked at when we had accumulated enough years of follow-up, we looked at baseline physical activity, their fragmentation index, and survival over up to 10 years. And what we saw that was for every 10th of a unit higher in fragmentation, so that's a 10%, so going from like 20% to 30% to 40%, there was a 49% higher mortality risk, which is quite a bit. We published in 2019. And more recently, Mauro Mediano, who was a visiting fellow from Brazil who was working with us, looked at this in the study of Latinos, which is a much larger population and a younger population. These guys are more middle-aged rather than older. And he saw a very similar effect here he looked at tertiles of fragmentation. Those in the highest tertile compared to the lowest tertile had a 45% increased risk of mortality over up to 10 years of follow-up. And he saw also that for each tenth of a unit higher, the risk increased about 22%. So that's not as high as we saw in the BLSA. Amal saw 49%, but again, these people are younger. So it does seem to inform us at older and at younger ages. Okay, there's another question in the chat. Susan just said, thank you. Cheryl said, has anyone correlated decreased mitochondrial function with the amount of daily activity? Yeah, we actually have some papers on that, Cheryl. I didn't include them here today because it's just a little bit complicated, but you can certainly go into PubMed and find them. But we do have one or two papers looking at mitochondrial function. Okay, so that also made us wonder about fragmentation and dementia. So going back to this paper that I showed you earlier that Anise led, thinking about daily fragmentation of activity and dementia, we know they have this difference in diurnal patterns. We know their patterns seem to be a little shakier, appear to be less stable. What does fragmentation and stability, what can we learn about that in terms of dementia? Okay, so this gets a little complicated, but I want to try to break it up and make it as simple as possible. And again, you can pull the paper if you're really interested and want to see it in more detail. But so Anise went into the NHATS data and she looked at dementia versus no dementia. So this is possible or probable dementia. And she saw that those with dementia had lower activity. So again, not surprising. And then she looked at their max 5 minutes per day in terms of activity. So that's looking at the intensity of their activity. How much acceleration did they generate in their maximum 5 minutes of activity per day? And those with dementia generated much less. So they were quite a bit less active in terms of their intensity. So they moved slower. They tended to do less. They had fewer active minutes per day. So this is a simple measure like steps or active minutes per day. They had 57 minutes per day less than people without dementia. So almost like a little over an hour. Intradaily variability. So again, people who are familiar with the sleep literature would be familiar with this. This is just looking at how variable the measure was day over day. Did their activity look differently? And we didn't see a difference by dementia status. And then we also looked at stability of activity, and we didn't see a difference. But we did see that their activity was about 5.7% more fragmented, which is a lot. So if you think back to those 10% increases in their associations, their increase with risk with mortality, a 5.7% greater fragmentation index is a lot. Is it clinically meaningful? We don't know yet because this is such a new metric, but we're working on trying to define that. Okay, let me see. We've got some more questions here. So just some thanks. Anonymous said, have you looked at oxygen intake for aging, oxygen desaturation in sleep and sleep apnea patients? So we've done some work associating this with things like VO2 max and laboratory measures of oxygen consumption and energy efficiency. I have a paper on looking at walking efficiency and physical activity fragmentation. But oxygen desaturation in sleep, we haven't done that yet. We're hoping to do that because one of the new devices, like I mentioned earlier, has an O2 saturation built into the device. And we are deploying that soon in the ERIC study and also in NHATS. So stay tuned. We hope to look at that soon. Okay, so this was looking at activity patterns by dementia, but Anise also looked at it by domain. So switching over now to the domains that make up dementia classification. So those of you who know cognition know there's executive function, there's orientation, and there's memory. So with those who had higher executive function tended to have more activity per day. And the same was true with orientation and memory, but the magnitude of that association was highest for those executive function. Then again, looking at their maximum 5 minutes per day, how much acceleration was generated during that time. So this is a measure of intensity. Those with higher executive function had more intensity, same with orientation and memory. So higher orientation performance, higher memory performance. We see that across the board. But again, executive functions seem to tell us the most. And then looking at active minutes per day, we see those with higher executive function. So one, I believe it's standard deviation increase in executive function was associated with 13 more active minutes per day, orientation 11 minutes, and memory 5 minutes. So, when we focus on dementia, it's often we focus on memory because that's what people really notice first is they can't remember things. But it also seems like executive function is probably the most informative. Then this was very interesting. We saw nothing with variability or stability with dementia, executive function, or memory, but we did see it with orientation. So these units don't have a lot of clinical meaning, but there was a significant association, meaning that those with higher orientation had lower intradaily variability. And so that means that their patterns of activity were less variable and they had higher stability. So it's kind of telling us the same thing. So the height of that curve, how stable was it day over day? It looked more similar for those with higher orientation compared to lower orientation. And then again, we see our friend fragmentation. So those with higher executive function had less fragmentation, which is a good thing. You want to be less fragmented. It means your bouts are longer. They had those with higher orientation had less fragmentation, and those with better memory had less fragmentation. So their activity was less broken up. So this is just a way of digging a little bit deeper. So like I said, if you just looked at total activity or active minutes per day or steps per day, you would be missing out on some of these more interesting findings that may help us understand how to observe and watch things going forward. Okay, so I want to finish by just touching on gait and ambulation because I know a lot of the engineers who may be on this are probably really interested in gait. I am not an engineer, so I'm going to issue that disclaimer. To start, I probably know just enough about gait mechanics to be dangerous, but I am very interested in it, and because I am very interested in walking speed as a predictor. And so a while back, I was working with Jacek Urbanek, who used to be here at Hopkins as faculty. He is an engineer by training. He actually left a few years ago to go into industry. And then Marta Karas, who was a PhD in biostats, she worked on this as part of her thesis. We went into the raw acceleration data to try to understand free living ambulation. So this is looking at walking, what walking actually looks like in the raw accelerometry data. And as you can see, it's remarkably consistent, right? If the person is walking and swinging their arm, it looks pretty much the same. It's pretty distinctive. This is how, for those of you who have an Apple Watch, when you're walking, it says, looks like you're walking. It knows it because it's rhythmic. And it's not perfect because if you're carrying something or holding something, you might miss some of that ambulation. But overall, it does a pretty good job. And so they developed this method called ADEPT. It's like adaptive empirical transformation patterns, something like that. I can't remember exactly what it stands for, but it has been published in Biostatistics in 2021. And basically, it's pattern recognition. So you have a calibration where the person walks in the lab. Maybe they do the 2-minute walk or something like that. So you can pick up on what walking looks like for that person. And then you say, okay, go ahead and do, go about your daily life. Go wear this for a week and then send it back to us. And so they developed a way to then go in and section the data and see how much of the data is related to ambulation. And this is really important because it gets at that question that I started with. So, how do we understand how people function in their own environment? So, this is from a paper that we published in 2022 from the STURDY trial. So, STURDY was a study on vitamin D supplementation in falls. Vitamin D actually did nothing. If you gave people vitamin D, did it prevent falls? It did not. But we did put accelerometers on everybody because we were also interested in how they moved. And so what you see here on the bottom of the screen are the traditional measures that are measured in lab or in clinic. So something like a 6-minute walk distance, their gait speed during the 6-minute walk, or their gait speed during the short physical performance battery, so like over 6 meters or 4 meters. And none of these things that we measured in the lab were predictive of falls at follow-up. However, we also derived some metrics from accelerometers. This is a similar accelerometer that people wore in Sturdy. It was an actigraph leap, and they wore it on their wrist. We looked at their cadence during the 6 minute walk because they wore the accelerometer during the 6 minute walk. So this is a in-lab measure, but it used the accelerometer. And we saw again, no association. It was a null association with falls. However, when we used the adept patterning, and looked at their cadence in the free living environment, it was predictive. So we saw that those who walked faster in their own environment tended to have a reduced risk of falls at follow-up. So this was about a 13% reduced risk of falls. And this was a sensitivity analysis, the blue, but you can see it, and it didn't really matter. It was just looking at some people who had done some other tests in lab as well. But the message was the same, that about 13% reduced risk for those who walked faster in the free living environment. So this is what I was getting at earlier, is that sometimes these lab measures, although we know they work well for some things, they may not work well for all things. So something like falls, it's extremely complicated, extremely hard to measure and understand because people fall for an incredible number of reasons. This is really getting at that because we're looking at how they move in their own environment. And so this was really interesting. And so this is also published if you're interested in looking more into the methods on how we did this. And so I just want to close with saying we have a lot of data. So if people are interested in talking more about some of these things, these are the studies we're currently monitoring older adults in. And so there are a lot of cohort studies, large cohort studies. They're mostly observational. Achieve was a hearing intervention study. So, and as I mentioned earlier, Sturdy was a vitamin D and fall study. So there are some interventions, but the bulk of the rest of them are observational work. But we collect this data in thousands of people, and we're hoping it will help us understand normative data going forward. So what's normal for older adults? How much should they move? What do their normal patterns look like? And so that when people deviate from that, it may be clinically useful. It may be able to tell us, hey, this person's at a higher risk of falls, or hey, this person has some kind of decreased activity that could be related to dementia or impending cognitive impairment, or it could be related to another chronic condition. And so that's the hope going forward. So I want to close and leave some time for discussion. So just acknowledging all the people who help contribute to much of the work that I showed you here today, and acknowledge my funding. And with that, I'm going to turn my camera back on and see here. It'll go. Okay, there we go. And so now I can see you guys again, and then I'm going to open up the Q&A and see if there are any more. I don't see, I think I answered most of these. So if there are any other questions, I'm happy to answer them now. I threw a lot at you guys. This research could be very powerful to help family caregivers convince hospice companies, yeah, not to graduate our loved ones from hospice and leave us with no hospice support as dementia. Yeah, and so I think that is really important to understand that. And we've shown in this work and in some other work that Amal's done independent of this, that it is possible to get people with cognitive impairment and dementia to wear these devices. And so I think that's really important. And I think that we're hoping, that these can be used for things like early detection as well as monitoring, right? Helping people, like you say, caregivers and things like that. So what are our next steps? Clinical meaning, normative data, understanding that. So, everybody always says we need more data, but we do need more data because this is kind of a newer area. Wearables is pretty new compared to a lot of scientific research. We need to understand it in larger swaths of the population. So definitely older people, what's normal for 60, 70, 80, 90. And once we know what's normal, then we can use it to hopefully inform clinical meaning. So let's see, what else? What recommendations do you have for senior living operators as a result of this research? So I think understanding mobility, how much people move when they move, is really, really important. So if we had the ability to monitor that, and you can use consumer devices to do this. Most of the research I've shown you here was done with those research grade devices, but you could do something very similar with a Fitbit or an Apple Watch or something like that if you were actually to give this to residents in a facility. You could do this. You could look at time of day differences. Are they up later at night? Are they wandering at night? Are they taking more frequent breaks in terms of their activity. It could inform a lot of things about their underlying health. How can we obtain the research data? So NHATS is publicly available, and you can go to the NHATS website and download it and use it. Some of the other studies, you just have to go to the study website and fill out a request. So like ERIC has that, a BLSA has that, I think Achieve has that. You can go in and request the data to use. Have I looked at postural stability data? No, not yet. And we need to. We need to understand. So that's another thing. Josh is asking about this. We need to combine this with gait lab data to understand it a little bit better. What is a measure of postural stability that we could derive from the wrist? Does it exist? I don't know. Um, and why am I concentrating on the wrist? Mainly because people wear it. So, like I said, we've used chest-worn devices, but people don't like them. They're uncomfortable. They're stuck to them with electrodes or some other kind of sticky tape. And people really don't like it. So the wrist is a place that people generally don't mind wearing the device. And so the compliance has generally been better with that. It has its faults because, wrist movement can be erratic, but we find that the magnitude of that more like I'm sitting here moving my hands, it's really actually a pretty small magnitude when you look at the data. And so compared to like walking or stepping or bigger types of activity, you get more acceleration with those. So these minimal hand movements don't interfere as much as people might think. Have you looked at light exposure wearables? I haven't specifically, but a lot of the sleep researchers have because they want to understand sleep a little bit better. And that can work well. Sometimes it can be complicated if somebody's sleeve comes down over their watch and might cover that sensor. But I think in general it works pretty well. But I personally haven't done that. Who will pay for the devices? Always a good question. I don't know. It would be nice if we can get to the place where Medicare would pay for these devices, but I don't know yet. Is the Trump administration affecting funding? I don't even want to answer that, Jose. I hate to say it, but not yet. And if I say that, something bad might happen, but it's always a concern. Would you suggest longer and easier exercises for older adults for cognitive health? More like so it's hard. More like HIIT training, so high intensity interval training. It's hard to say because it depends on their functional ability. Any kind of movement is going to help, right? It's not all about MVPA, right? So moderate to vigorous physical activity, things like that. If they can do it, great. But the problem is if you have somebody who's healthy enough to engage in high intensity interval training, they're probably fine, right? It's the people that are older, that are more likely to be frail, that have cognitive problems, vision problems, hearing problems. Those are the people that can't do those kinds of things. And so understanding how they move at a lower level can actually really be informative. Okay. Have you found differences in activity by geographic region or rural versus urban? So we haven't done it, and I think it's a great question. So actually in NHATS, there is a rural versus urban indicator in the participant file, and then you could combine that with the accelerometer data and answer that. If you wanted to do more specific geographic, like census tract type analyses, you can do that as well, but it's restricted data. You just have to apply for it because with geographic data, we have to be more careful, and those analyses have to be done in an enclave. But it's a great question. There's so much that could be done with this data. We really just scratched the surface. So I encourage a lot of people who are interested in this to, seek data out, definitely look into it and think about, these new and exciting ways that you can look at the data and really do exciting things. Do you see the segmentation regarding BMI and disease and comorbidity? Yeah, I mean, definitely those who are, I think we have a paper where we looked at peripheral artery disease and those who had more PAD or who had PAD versus just different regular, we looked at ankle brachial index. So if your ABI was normal versus high or low, depending if you're looking at the high ABI versus low ABI, because it kind of can be a J-shaped association, we did see that those people were more fragmented. And so it's the same kind of thing. It's decreased endurance, it's decreased capacity, it's having to stop and rest more. It could be intermittent claudication with something like peripheral artery disease, although we didn't see an association with leg pain. But again, it could be for a lot of reasons. And so I think this is good and bad, right? We can detect that something's wrong, but a lot of times it's non-specific. And I think that's a lot of the reasons that mobility might not get the attention it deserves in the clinic because you can say, okay, this person's slow or okay, this person's less active than they should be. But a lot of times it's non-specific. We don't know why. You still have to dig deeper and understand what's clinically wrong. But I think if we can demonstrate that mobility and activity change often before a clinical diagnosis, that makes it an early detection tool that can actually really help us understand disease earlier in the processes where it may be more likely to be treatable, regardless of what it is, whether it's vision loss, whether it's hearing loss, whether it's cognition, whether it's cardiovascular disease, regardless of what's causing it, if we can detect it earlier with something like a wearable, whether it's through mobility or for oxygen saturation or heart rate or any of these things that can come from these wearables, I think it can really help us push the envelope in understanding and advancing health in terms of promoting health, but also detecting changes in health. Have you noticed the effect of leg cramps? Are they related to exercise, aging, and weight? I don't know. I don't know the answer to that. It's a good question, but it's not something we've looked at. Um, okay. Well, unless there's any last questions, I think I've talked quite a bit. So I think I can stop sharing. Um, yeah, and let you guys get back to your day.
Thank you, Jen.
Yeah, thank you very much. Thanks for signing in, everyone. Have a good one.